Whenever we make decisions using sample data, there is always some uncertainty. Because of randomness, we can end up making incorrect conclusions. Hypothesis testing makes this idea explicit by recognizing that errors are possible and even expected in the long run. There are two possible truths in hypothesis testing. Either the null hypothesis is actually true or it is actually false. At the same time, there are two possible decisions we can make. We either reject the null hypothesis or fail to reject it. When we combine these possibilities, we see that there are two main types of mistakes we can make. These are called type 1 errors and type 2 errors, and understanding them is central to interpreting hypothesis tests correctly. A type 1 error occurs when we reject the null hypothesis even though it is actually true. This is often called a false positive because we are concluding that something is happening when, in reality, nothing has changed. For example, we might conclude that a drug is effective when it actually is not, or that a marketing strategy increases sales when it has no real impact. These are situations where we incorrectly detect an effect. The probability of making a type 1 error is called the significance level, often denoted by alpha. Common choices for alpha are 0.05 or 0.01. This value is chosen before conducting the test. If we choose alpha equal to 0.05, we are saying that we are willing to incorrectly reject a true null hypothesis about 5% of the time in the long run. This reflects how much risk we are willing to take for a false positive. A type 2 error occurs when we fail to reject the null hypothesis even though it is actually false. This is called a false negative because we miss a real effect that is present. For example, we might conclude that a treatment does not work when it actually does, or fail to recognize a business strategy that truly increases profits. In these cases, we miss something important. The probability of a type 2 error is denoted by beta. Unlike alpha, beta is not directly chosen, but depends on factors such as the sample size, the variability in the data, and the size of the true effect. Closely related to type 2 error is the concept of power. Power is defined as 1 minus beta. It represents the probability that we correctly reject the null hypothesis when it is false. A test with high power is desirable because it is more likely to detect real effects when they exist. A low power test, on the other hand, is more likely to miss those effects. There is an important trade-off between type 1 and type 2 errors. If we reduce alpha and become more cautious about false positives, it becomes harder to reject the null hypothesis, which increases the chance of a type 2 error. On the other hand, if we increase alpha and make it easier to reject the null hypothesis, we reduce the chance of a type 2 error, but increase the risk of a false positive. This leads to a key idea. We cannot minimize both types of error at the same time unless we increase the sample size. Larger samples help reduce both types of error simultaneously. There are several ways to reduce errors in practice. Increasing the sample size reduces variability and improves our ability to detect real effects. Using more precise measurements and controlling variability also helps improve the reliability of our conclusions. A helpful way to understand these ideas is through a legal analogy. In this analogy, the null hypothesis represents innocence. The alternative hypothesis represents guilt, and the data represent the evidence presented in court. A type 1 error corresponds to convicting an innocent person, and this is considered a very serious mistake, which is why both the legal system and statistical testing procedures are designed to make this outcome unlikely. A type 2 error corresponds to failing to convict a guilty person. In this case, the evidence was not strong enough to reject the presumption of innocence, even though the person was actually guilty. Power in this analogy represents correctly convicting a guilty person. A high-power test means that when there truly is an effect, we are likely to detect it. The legal analogy highlights the balance involved in hypothesis testing. We begin by presuming innocence and require strong evidence to reject that assumption and try to avoid convicting the innocent while still detecting guilt when it exists. If we make it extremely difficult to convict by choosing a very small alpha, we reduce wrongful convictions but increase the chance that guilty individuals go free. If we make conviction easier, we increase power but also increase the risk of wrongful convictions. We can summarize all of this in a table. If the null hypothesis is true and we reject it, we commit a type 1 error. If the null hypothesis is false and we fail to reject it, we commit a type 2 error. The other two outcomes correspond to correct decisions. In the big picture, hypothesis testing is not about certainty. It is about managing risk. We carefully choose our significance level and design our studies to balance the risks of different types of errors. For example, in a medical trial, a type 1 error might mean approving an ineffective treatment, while a type 2 error might mean rejecting a treatment that actually works. Both have serious consequences. In quality control, a type 1 error might lead to shutting down a production line that is functioning correctly, while a type 2 error might allow defective products to reach customers. In biological research, a type 1 error might lead to pursuing a gene that is not actually important, while a type 2 error might cause us to miss a gene that truly matters. To recap, a type 1 error is rejecting a true null hypothesis. A type 2 error is failing to reject a false null hypothesis. The significance level controls the probability of a type 1 error, and power represents our ability to correctly detect real effects. Ultimately, hypothesis testing helps us understand and manage uncertainty. It does not eliminate error, but it gives us a framework for making informed decisions in the presence of randomness.